You're here because, like us, you believe that the best knowledge is often tucked away inside the biggest mysteries. And today we are heading out on, well, a cosmic adventure. It's a kind of an intellectual shortcut to understanding one of the most incredible scientific feats of our time. We're talking about capturing an image of the uncapturable.
We are diving deep into the world of Heino Falcke, who is this award-winning astrophysicist who was just so central to the Event Horizon Telescope project. And our guide for this is his amazing book, Light in the Darkness, Black Holes, the Universe, and Us.
And this isn't just a science textbook recap. Falk's book gives you this really awe-inspiring look at the decades of personal challenges, the insane amount of global teamwork it took, and, the deep existential questions that just sort of exploded into view when we finally saw it.
Yeah, the whole idea of the book is this beautiful paradox. That the black hole, which is, the ultimate symbol of darkness in the universe, it actually gives us the brightest insights into what existence is, what gravity is, the very fabric of reality.
So that's our mission today. We're going to trace that entire journey chapter by chapter. We'll start with the pure theory and go all the way to the photograph, and then deal with the philosophical fallout.
Let's do it.
Okay, so let's start where every big scientific quest does, with the idea itself. Chapter 1, Exploring the Infinite Depths of Black Holes. This chapter really defines these cosmic monsters. So for everyone listening, let's just refresh on the basics. What makes a black hole so different from, say, any other dead star?
Well, it really comes down to gravitational collapse taken to its absolute most violent extreme. Black holes are what's left over when a truly massive star dies.
Way bigger than our sun, right?
Oh, way, way bigger. Once that star runs out of nuclear fuel, the outward push just stops. And gravity, which has been trying to crush it the whole time, finally wins. It collapses the core inward and it doesn't stop. It just keeps crushing and crushing until all that mass is packed into a space that is, well, infinitesimally small.
The singularity.
The singularity. And that's the point where our physics just completely break.
It just gives up.
It just gives up. At the singularity, you have infinite density, and the forces are so extreme that our entire rule book for the universe, Einstein's general relativity, it just stops giving you sensible answers. It's a literal tear in the fabric of cause and effect.
But the part that we as observers really care about isn't the singularity itself, because we can't see it. It's the border around it.
Exactly. That's the event horizon. And that's the crucial part. It's the boundary where the escape velocity, the speed you'd need to get away, becomes faster than the speed of light.
And since nothing can go faster than light,
nothing gets out. Anything that crosses that line, a star, a planet, a photon of light, it's trapped forever. And that's what makes them black. They don't emit any light. They don't reflect any light. They are, for all intents and purposes, invisible.
It's just amazing to think that this object, defined by not having light, was predicted purely with math, like 100 years ago.
Yeah.
Could you walk us through that history? It starts with Einstein, but he wasn't even sure they were real, was he?
Not at all. He was actually pretty skeptical. His theory of general relativity in 1915 described gravity as this curvature of space-time, but he thought the idea of something so dense that it would cause this kind of collapse was just, a mathematical quirk. But then almost immediately, a guy named Carl Schwarzschild found an exact solution to Einstein's equation.
While serving in World War I think.
Yeah, in the trenches. It's incredible. And his solution was revolutionary because it described the space-time around a simple, non-rotating mass. And buried in his math was a specific radius, what we now call the Schwarzschild radius, where the equations just went haywire.
They broke.
The math suggested the curvature of space-time became infinite, and that radius he calculated, that defines the exact size of the event horizon. That's what took the black hole from maybe a weird idea to a direct theoretical consequence of general relativity.
But it still took a few decades for people like Penrose and Hawking to really cement the idea in the mid-20th century. What did they add to the picture?
They were hugely important. Roger Penrose proved that singularities weren't just like an accident of using a perfectly spherical star in the math.
Yeah.
He showed they were an inevitable result of gravitational collapse, period.
No matter what shape the star was.
Exactly. And then Stephen Hawking came along and added another layer of mind-bending complexity with Hawking radiation. He suggested that because of weird quantum effects right at the edge of the event horizon, black holes aren't completely black. They can actually, very slowly, leak energy and over trillions of years, evaporate.
Wow.
Yeah. And that idea really turned them into dynamic, evolving parts of the cosmos, not just cosmic drains.
So that brings us to Falcke and his colleagues. Why did they see black holes as these essential things to study, not just weird cosmic vacuum cleaners?
Because they're the ultimate laboratories for extreme physics. I mean, that's what Falk calls them. We can't create these conditions on Earth. We can't make something with that much gravity, that much density. Black holes are the only place in the universe where we can test if Einstein's theories hold up under the most extreme pressure imaginable.
Pushing general relativity to its absolute breaking point.
Precisely. And since we now know that supermassive black holes are at the center of pretty much every big galaxy, including our own, understanding them is fundamental to understanding how the universe itself is built. And that need to test the theory, that's what drove them to start the Event Horizon Telescope project.
Which is a perfect lead-in to the next part of the story, Chapter 2, the Event Horizon Telescope Capturing the Invisible. The challenge here was just astronomical, visualizing something that's defined by its invisibility. What kind of resolution are we talking about here?
The difficulty is just hard to overstate. The black hole they were targeting, M87, is huge, but it's 55 million light years away. So from our perspective on Earth, it's unbelievably tiny.
Falcke has a great analogy for this, right?
He does, and it's perfect. He says achieving the resolution they needed was like trying to read the date on a quarter in Los Angeles while you were standing in New York City.
That's impossible.
Yeah.
You need a telescope the size of a planet.
Exactly. A single telescope dish that powerful would have to be wider than the Earth itself. So it was physically impossible to build one.
So if you can't build one, you have to.
Yeah.
What, fake one? Create a virtual one? This is where very long baseline interferometry, or VLBI, comes in. How on earth does that work?
It's an absolutely brilliant technique. Instead of one giant dish, they used a whole network of radio telescopes scattered all across the globe. You've got one in Chile, one in Hawaii, Spain, even the South Pole.
Okay.
Each telescope on its own just captures a tiny little piece of the radio waves coming from the black hole. But, and this is the genius of it, if you combine all of those little data fragments and you correlate them perfectly, the resolving power you get is the same as a single telescope with a diameter equal to the farthest distance between any two telescopes in your network.
So they basically turned the entire planet into a single telescope lens.
That's exactly what they did. They created a virtual Earth-size telescope.
That sounds like an absolute technical nightmare. I mean, what do you need to make sure all those signals from thousands of miles apart actually line up and act like they came from one instrument?
Synchronization. Absolute, perfect, unforgiving synchronization. They're collecting waves, so the crests and troughs of those waves from every single telescope have to be aligned to within a fraction of a wavelength.
Which means the timing has to be, what?
Down to the nanosecond, over thousands of miles. To do that, they had to install these incredibly precise atomic clocks at every single observatory, no matter how remote.
Okay.
We're talking hydrogen maser clocks.
The kind that lose like 1 second every million years or something.
That's the one. These clocks were non-negotiable. They allowed every single data point to be time-stamped with incredible precision. And then later in processing, they could use the tiny, tiny time delays, the phase differences between when a wave hit the telescope in Chile versus the one in Hawaii to mathematically build the picture.
The logistics of just that part alone are staggering. But it wasn't just the clocks, right? What other hurdles did they face?
Well, first, the frequency they had to observe at was super high, around 230 gigahertz. You need that high frequency to cut through all the gas and dust around the center of a galaxy. But the downside is that your instruments have to be unbelievably cold to work at that frequency.
How cold?
Almost absolute zero, like minus 269 degrees Celsius. And you have to maintain that cryogenic environment in some of the most remote, difficult places on Earth, like a desert high in the Andes. It's a huge engineering challenge.
And then there's the data. Falcke writes about how the sheer volume of it was too much for the internet back in 2017.
Oh, yeah. We're talking about petabytes of data.
Yeah.
That's thousands of terabytes. The observatories were recording data at a rate equivalent to streaming thousands of 4K movies at the same time. There was no way to send that over the internet.
How did they get it?
They flew it. They physically recorded everything onto huge stacks of special rugged hard drives and then shipped them by plane from all over the world to 2 central processing centers in Germany and the US.
You're kidding. They put years of irreplaceable scientific data in the mail. I can't even imagine the anxiety.
Falcke says it was palpable. Think about it. If the shipment from the South Pole telescope got lost or damaged, the entire project could fail. The resolution of their virtual telescope would just collapse. It was this crazy race against time and logistics.
And they aimed this whole planet-sized operation at the black hole. in the M87 galaxy. Why M87? It's 55 million light years away. Why not the black hole at the center of our own galaxy, Sagittarius A star? It's so much closer.
That's a great question, and it's a really crucial detail. The ultimate prize was always Sagittarius A star, or SGRA, but for the first attempt, M87 was actually the better target.
How so?
Even though SGRA is closer, it's also smaller. The ratio of their mass to their distance means they actually look about the same size in our sky. But the key thing is that the center of our own galaxy is a mess. It's full of turbulent gas and dust that's constantly blurring our view of SGRA. M87, on the other hand, is a much cleaner, more stable, and quieter target. It was the perfect place to test if this crazy idea could even work.
So once all the hard drives finally arrived safely, the last big step was turning all that noisy, fragmented data into a single picture. And that took some serious algorithmic magic.
This is where computer science really became the hero of the story. Falcke gives a lot of credit to researchers like Katie Broman and her team who developed these really sophisticated imaging algorithms. Because you have to remember, the raw data from VLBI doesn't look like a picture at all. It's just a complex jumble of correlations.
It's just numbers.
Just numbers. The algorithms had to filter out all the noise from the atmosphere, fill in the huge gaps in the data because they only had a handful of telescopes, not a solid dish, and then rebuild a picture that made sense based on the rules of general relativity.
Which brings us to that incredible moment in April 2019. This is chapter 3. The first image of a black hole, a momentous achievement. Let's talk about what that iconic image actually showed us.
It's stunning because it looks exactly like the theory predicted it would. You have this dark central region, that's the shadow, and it's surrounded by this bright, glowing ring of light.
And that ring is the light in the darkness.
Exactly. That ring is radiation from superheated gas and plasma that's whipping around the black hole at almost the speed of light. It's the last scream of light from matter just before it crosses the event horizon. And you'll notice the ring isn't perfectly even. It's brighter on one side.
Yeah, why is it brighter on the bottom in the picture?
That's one of the coolest parts. It's a direct confirmation of Einstein's theories. The material on the ring that's moving towards us as it orbits gets its light boosted and brightened because of the Doppler effect. The stuff moving away from us gets dimmed.
Relativistic beaming.
Exactly. Seeing that asymmetry was visual proof that this stuff was moving at these insane relativistic speeds, confirming the black hole's immense gravitational pull.
Now, we should probably clarify something. The dark part, the shadow, isn't the event horizon itself, is it?
That's a great point, and a key one for anyone interested in the physics. The shadow is the region where we see no light. But it's actually bigger than the event horizon. The gravity is so intense that it bends the path of light, even light that's just grazing past the black hole. This gravitational lensing effect actually magnifies the darkness, making the shadow appear about 2.6 times bigger than the event horizon itself, and measuring that size was a critical test.
A test that general relativity passed with flying colors.
With flying colors. I mean, it was the strongest visual evidence you could ever ask for. For the first time, we could actually see that this boundary, the event horizon, was real. And by measuring the size and the shape of that shadow, the team confirmed that it matched the predictions made by Einstein's equations a century ago, but under conditions far more extreme than he could have ever tested.
And Falcke keeps coming back to the collaboration in this chapter, framing it as, just as important as the technology.
Because it was. The problem was just too big for one group. You needed radio astronomers to run the telescopes, physicists to understand the plasma, and computer scientists to build the algorithms and process the data. It wasn't just countries working together, it was whole fields of science having to learn to speak each other's languages. That fusion of expertise was the only reason it succeeded.
And in doing so, it took the black hole from this abstract concept on a blackboard and turned it into something real. Something anyone on Earth could look at.
That was a huge part of its power. It just captured the world's imagination. It made this extreme, distant part of the cosmos feel tangible and accessible. And it showed a whole new generation that humanity can solve impossible problems when we work together.
So now that we have the picture, the book pivots from the science of what we can see to the philosophy of what we can't. This is chapter 4, Bridging Science and Philosophy, the Nature of Space and Time. How do black holes just completely wreck our normal everyday intuition about how reality works?
Our intuition is built for, Earth. It's built on low gravity, slow speed, Newtonian physics, where time ticks by at the same rate for everyone, and space is just the static, empty stage. Black holes they shred that rule book.
Yeah.
They force you to accept that space and time aren't separate things. They're woven together into space-time, and this fabric can be stretched and squeezed and warped by gravity. Near a black hole, time for an observer literally slows down. Space itself is dragged around by the black hole's spin. It's a universe that is just so much weirder than our brains are built to handle.
And the event horizon itself.
Yeah.
It's not just a physical boundary, it's a philosophical one. A boundary on what we can ever know.
Yes. Falcke makes a huge point of this. The event horizon represents a fundamental limit to human knowledge. Any information about what falls past that point is shielded from us forever. And he argues that this is a really profound lesson. It forces scientists, and all of us, to accept that the universe might not be completely knowable. It demands a certain humility.
A humility that runs right up against one of the biggest paradoxes in all of physics. The information paradox.
Yeah.
Can you break that down for us? How does a black hole seem to violate like a fundamental law of the universe?
Okay, so a basic rule in both classical and quantum physics is that information is never truly destroyed. It might get scrambled and hard to read, but it's always conserved. If you know everything about a system right now, you can, in theory, figure out its entire past and future. That's determinism.
Right.
The paradox is that when something falls into a black hole, all of its complex information, what it was made of, its shape, everything, seems to just disappear.
Yeah.
The black hole itself is only defined by three simple things: its mass, its spin, and its charge. All that other information seems to be lost.
And if it's truly lost, then cause and effect, predictability, it all kind of breaks down.
Precisely. And it gets worse. If Hawking radiation makes the black hole evaporate, where does the information go? The radiation that comes out seems to be random thermal energy with no information in it. If the information is gone forever, it violates quantum mechanics. And solving this paradox is probably going to require a theory of quantum gravity, which is the holy grail of modern physics. The black hole isn't just an object, it's the physical embodiment of this huge crisis in our understanding.
And when you think about that, about these cosmic monsters, it should make you feel tiny, but Falcke argues it's a dual feeling. It also shows how great we are.
He really does. On one hand, yes, you look at a supermassive black hole and you feel an incredible sense of cosmic humility. Our problems seem so small. But on the other hand, you have to marvel at the fact that these tiny creatures on a small rock humans could figure all this out. That through pure thought and teamwork, we could build a machine to take a picture of it.
So studying black holes becomes a kind of mirror.
A perfect mirror. It's objective science, but it's also a subjective philosophical journey. It reflects both our limitations and the incredible depth of our own curiosity and ingenuity.
Let's zoom back in on that ingenuity now and the people behind it. Chapter 5, the human element, collaboration, and perseverance in scientific discovery. Falcke makes it really clear that this story is as much about people as it is about physics.
Oh, absolutely. He spends a lot of this chapter talking about the human cost, the decades of dedication. This wasn't a quick project. This was a narrative of people dedicating their entire professional lives to a single, audacious, and frankly, seemingly impossible goal, often with very little funding or support in the early days.
And the collaboration. It wasn't just a few universities, it was global. How did they manage to build that kind of trust across cultures and continents?
The trust was really forged in the fire of the problem itself. The science was the universal language. They had experts from dozens of institutions, all with different ways of doing things, different funding cycles, different languages. But the scientific goal was so hard and so clear that it forced them to find a way to work together. Falcke even says that their disagreements often led to the most creative breakthroughs.
And the perseverance to just keep going, even when things went wrong.
It had to be immense. There were so many setbacks. Instruments would fail in the extreme cold of the South Pole. Weather wouldn't cooperate across all the sites. Data would get corrupted. They had to be so resilient, just constantly innovating and problem solving for years and years with absolutely no guarantee that they would see anything at the end of it all.
That story about shipping the hard drives really captures that pressure, doesn't it?
It really does. I mean, can you imagine being the young scientist at one of those remote sites? And it's your job to make sure this box of hard drives containing a piece of a multi-million-dollar global experiment makes it safely across the world. The human pressure at every step was just enormous.
So what's the bigger lesson Falcke wants us to take from the EHT success?
That it's a blueprint. It's a testament to what humanity can achieve when we embrace open-mindedness and cooperation. It proves that our biggest challenges, whether they're scientific or otherwise, can be overcome when we pool our talents and work towards a common goal. He calls the image a shared triumph for all humanity, and I think that's exactly right.
So after achieving the impossible, the story doesn't end. It just opens up new questions. We're at Chapter 6, looking beyond the future of black hole research. The image was a beginning, not an end.
Not at all. In fact, it just made the remaining mysteries even more tantalizing. We've seen the edge, but we still have no idea what's happening at the absolute center. What is the singularity, really? Is it this point of infinite density that general relativity predicts? Or does some new exotic physics kick in at that scale and prevent a total collapse?
This is where the two biggest theories in physics have their showdown.
It's the ultimate showdown. General relativity, which governs gravity and the large-scale universe, has to somehow merge with quantum mechanics, which governs the small scale. The singularity is where they have to meet. And future research is all about finding clues that could lead us to that unified theory of quantum gravity.
And to find those clues, we need better tools.
Yeah.
What does the next generation of black hole imaging look like?
The next big goal is to go from a single snapshot to a movie, to actually see the dynamic behavior around the event horizon in real time, to watch gas swirl in, to see jets of energy being launched. Yeah. And to do that, you need even better resolution. So the plan is to add more telescopes to the EHT network, and eventually to put telescopes in space. A space-based VLBI array would be the dream. It would eliminate the blurring from Earth's atmosphere and give us unbelievably sharp images.
And it's not just about taking pictures anymore. We have a whole new way to study them now with gravitational wave astronomy.
That's the other huge revolution happening right now. Observatories like LIGO can now hear the ripples in space-time gravitational waves that are created when two black holes collide and merge. It's a completely new sense for exploring the universe.
So we can see them with radio waves and hear them with gravity waves.
Exactly. It's called multi-messenger astronomy. And it lets us study black holes that are otherwise completely invisible, the ones that aren't actively feeding on gas and glowing. The next generation of gravitational wave detectors could discover whole new types of black holes we don't even know exist.
And maybe even the oldest ones, the ones from the beginning of time.
That's one of the most exciting possibilities. The search is on for what are called primordial black holes. These are theoretical black holes that might have formed in the chaotic moments right after the Big Bang, not from collapsing stars. If we found one, it would be like finding a fossil from the birth of the universe.
Just incredible. So that brings us to the final reflections. Chapter 7, Light in the Darkness Reflections and Final Thoughts. After this entire epic journey, what's Falcke's final message about what this all means?
He really sees the photograph as a symbol of the human spirit. It represents our resilience, our creativity, our ability to solve problems that seem completely impossible. It's proof that our curiosity can literally push the boundaries of the known universe.
And that theme of unity comes back again very strongly.
Very strongly. He holds up the EHT collaboration as a model for how humanity should tackle its biggest problems. The black hole, this incredibly destructive object, ironically ended up bringing people on Earth closer together.
It also forces us to confront that duality of our own existence, doesn't it?
It really does. You're forced to recognize how tiny and fragile we are in the grand cosmic scheme. But at the same time, you have to celebrate the fact that our minds are powerful enough to comprehend these forces and even picture them. We are both insignificant and magnificent, and the black hole makes you feel both of those things at once.
So the title, Light in the Darkness, it's more than just the literal light from the plasma ring.
Much more. The light they captured is a philosophical beacon. It symbolizes knowledge itself. It shows that even when we stare into the darkest, most mysterious corners of the universe, the act of looking, the act of seeking knowledge, illuminates our own understanding of our place in it all.
And so the final message is that this journey of discovery, it never really ends.
That's it, exactly. Falcke closes by saying the image is a huge milestone, but it's not the destination. The whole process, the struggle, the teamwork, the final revelation, that's what science is. It's a continuous, never-ending quest. And that quest to light up the cosmos is what ultimately reveals the boundless possibilities within ourselves. So, to kind of wrap up Falcke's powerful journey, Black holes, these symbols of absolute darkness and the extreme edge of physics, they paradoxically became the brightest stage to test 100 years of theory. They gave us this stunning confirmation of general relativity, while at the same time forcing us to think about the absolute limits of what we can know.
And our goal with this deep dive was really to give you that full picture, not just what the image is, but the incredible story of why getting it was such a game changer for science, for technology, and for human collaboration. It's a story of extremes, really cosmic, logistical, and intellectual.
And as we finish, here's a thought to take with you, one inspired by the decades of persistence that the EHT team showed. If the universe teaches us that we have to keep pushing against seemingly impossible boundaries to learn anything new, what boundary in your own world, your own work, or your own understanding are you ready to start pushing against next?
Something to think about. Thank you for joining us on this deep dive. We'll see you next time.